All right, welcome back to the Neuro Symbolic Channel. This is part two of my interview with Luciano and Sammy, two of the authors of Logic Tensor Networks. In this part of the interview, we're going to actually talk a little bit about their work. And if you want to learn more about all the technical details of Logic Tensor Networks, we do have a series of videos as well on the channel. So let's start out. And whichever of you wants to answer this first, just briefly describe logical tensor networks at kind of a high level.
Should we start or?
Go ahead.
Yeah. So in very few words, logical tensor network is just a neural network where you encode some logical formula into the loss function, and you try to train the network to satisfy as much as possible that logical formula. And the point is that the output of the neural networks are used to establish the truth value of the predicates that compose this formula, and then you can compute the truth value of the formula by simply applying the semantics of the connectives and quantifiers. And this gives you the final result on how much your formula is satisfied. And the training is just try to learn the basic neural network so that such a truth value is maximally satisfied.
No, I think that was really a nice, concise description. Along those lines, I think one thing, actually two characteristics I found interesting with it is, one, your decision to use fuzzy logic as a way to propagate the gradient back through the network. And two was your decision to your layers of parameterization lied below the actual definition of the logical symbols, and you use the term grounding that associates the logical constants with the underlying neural structure that builds that up. In this, both of these, I think, are different than other design approaches. So like neural ASP, they do not propagate the gradient through the logic to the network, and logical neural networks, they parameterize the operators instead of the underlying logical constructs. So what drove those decisions?
It's very difficult to say, but I think it's the how can I say, the fact that I was aware for a long time during my career of knowledge representation that I was manipulating symbols without any meaning associated, real meaning associated to these symbols. For example, sometimes I was reading paper, something like that contains predicates like father X and Y implies parents X and Y. And this paper assumes that this implication was magically true, okay? Just because you call it father and parent. But the point is that without symbol grounding, without grounding these symbols to the reality, to the perception that concerns the relationship between X and Y, you will never get these out. I mean, you can call these two parents and father with two completely different names, like Pippo and Pluto, whatever, just two random words, and the theory will remain the same. But I was fascinated by giving meanings to that symbols, and that's why I also call them groundings.
Yeah, I thought that was an interesting choice of words. I mean, my background is logic programming, and when I first read that you were calling that grounding, I actually got a little upset because I'm just used to the idea of moving from non-ground atoms to ground atoms, and that process being called grounding.
Yeah.
Um, Now I know in things I've read since then why you've made that choice. But maybe if you could describe, why you use the word grounding in this way.
Because I was fascinated by this idea of symbol grounding. So you ground, or I could have used also anchoring, but grounding, I like it more. There is a paper, I think in 2001, or I can't remember the author, that was introducing this idea of symbol grounding, which is the problem that an autonomous agent has to create a correspondence between a symbol, an internal symbol that it uses to represent knowledge, like in a logic program, and the perception that it has about that object. Okay, and this connection is called grounding, and that's why I call it grounding. Okay. Also, the name was, I think, lately used by the people who did IMAD and language alignment. And one is called the textual grounding. It's a task in vision that aligns a text of a caption, the elements of a caption, to the bounding boxes of the objects in an image.
Oh,
so this is also called grounding, okay? And I was aware of the confusion that I will have created by the people, by the logicians that use grounding in the terms of instantiating one variable into a constant. But the constant itself is just a symbol, and it needs to be grounded to the reality itself. John is just a symbol. You have to ground it to your capability of recognizing John, of saying, okay, this is John, and this one is not John. Otherwise, that remains a symbol.
No, and I think this was something I found really interesting. Also for our viewers, I'll put a link to one of our videos about symbol grounding. And we've looked into this in other frameworks as well, like SatNet. So Sammy, in part one of our interview, you mentioned that when you got exposed to LTN, you had some ideas of how to extend it. What were those ideas? What extensions did you contribute to this framework?
So when I started working with LTN, I started trying to, as I was saying, spin a few experiments. And to do this, I tried a bunch of the examples that were at the time implemented in the LTN repository. And the limitation I found is just that some of the examples didn't learn, even though the logic made a lot of sense. The symbol grounding made sense. The neural network couldn't learn. And it took me a while, but I figured out kind of at the same time as some people from the Vrij University from Amsterdam.
Oh, yeah, Emil van Krieken.
Yeah, right. They published a very, very interesting work where they analyzed the gradients, how the derivatives work for different fuzzy operators. And with this insight, I started to look in LTN in a very different way. I sort of like forgot about the semantical part and so on, and just looked at it as a loss function. And this is where I started to contribute to LTN, because I noticed why some stuff were not working. Why some operators work better than the others, and what I could modify again in those operators to work even better. And doing that, we managed to have good results in all the examples, and get to the publication of the article a few months after. Yeah.
Oh, okay. So you're the one that came up with that little trick to address the boundary case for like the product T norms and stuff like that.
Right. And of course, always with feedback from Luciano and Michael Spranger, and of course Arthur Garces. But yeah, so my contribution was this stable operators, also the guarded quantification, which was a trick to avoid having zero gradients in too many parts of your computational graph. It's just like you reduce the complexity of the computational graph by using guarded quantification, and and also a re-implementation of the framework in TensorFlow 2, because at the time it was in TensorFlow 1 and everybody hated TensorFlow 1. Everybody was switching to PyTorch, and so I helped re-implementing it in something that was a bit more usable, TensorFlow 2. Yeah.
Oh, okay. Would there be any plans to port LTN over to PyTorch?
Yeah, actually, there's a few people have made this port, including some students from Luciano. So now we have in the official repository for logic tensor networks, one of the sub directories is for the PyTorch implementation. When we test out new ideas, at least from my side, I work on the TensorFlow version, but the PyTorch implementation is perfectly stable with what was in the and has everything implemented that was in the article back then.
Oh, really cool. Luciano?
Yeah. No. If you want, I can introduce the student.
Okay.
Okay, but that's okay. I think that the Sami's contribution was really fundamental to make it, an idea more practically used and introduce a lot of important enhancement to make this idea really working. Otherwise, it would have been just an idea and stay there. So I was really thankful to Sami for this.
Yeah, I have a feeling, I think between seeing those results and the differentiable fuzzy operators paper that you mentioned, I think there's going to be a lot of research that is going to be along those lines in how do we do things to tame gradient descent in order to drive better neurosymbolic results. I think that's going to be a big area, and there's going to be a lot of empirical studies, a lot of things like these lists of operators and how they perform. So along the lines of results, what do you view as maybe some of the more exciting results that you think bodes well for the future of LTN, Luciano?
Well, one of the themes that we are planning to work, and we are starting also to work, is to extend the LTN approach to data that are more structured, like temporal data or graph data, where essentially you have you have an underlying structure of the data that and what you do in one particular point influences also the other. In particular, the temporal part is really important, and this, of course, allows us to impose a constraint and to reason about temporal logic, temporal evolution, and things like this.
Oh, so would you be looking to support like something like LTL, or would this be something different?
That's one option. There is already some work considering LTL, in particular LTLF, some work of PhD students in Rome, I think. We were more interested in considering more, say, first-order logic approach that consider intervals, Allen relationship between intervals, and things like this.
Oh, okay, really cool. So just to wrap up this first part of the interview, what do you, kind of looking beyond sort of near-term research goals, such as these temporal extensions, what do you see as the future of LTNs in the field of AI? What role do you see them playing?
Well, it's a very difficult question to answer. I cannot predict the future, to be honest. I think that ideas and systems somehow they go from person to person, and they influence the thought or the idea of other people. And my understanding is that so far LTN has done very well this job, in the sense that papers about LTN are not only by us, and after the first publication of LTN, there has been many people who start considering to enhance, to develop different systems on neurosymbolic integration. I think that LTN was one of the first. And so these, so what will happen in the future, I really don't know. I can see the past, and I see that LTN influences quite a lot the literature on neurosymbolic integration. And I hope it will influence more by new ideas. And that's the only thing that I can say.
What are your thoughts on this, Sammy?
Yeah, it's a very good question. So one thing I've noticed in working with LTN in the industry is I really think LTN and maybe neurosymbolic AI in general can help connect AI models with experts of a given model, a given domain, sorry. So that's in the context of knowledge-aided learning. So all those concepts of constraints and so on, I think it can sort of bridge AI and experts that already are in the field. And another thing, it's not about learning here, but I think in general it can give some structure to neural networks. So here it's works that do things like complex querying or explainability and so on. I'm hoping to see LTN on other neurosymbolic methods sort of be something on top of all those ChatGPTs and so on to kind of like make them work together. And then I think that to get there, we need some huge AI breakthrough that uses neurosymbolic, so that someday something like AlphaGo, but that uses a neurosymbolic method. And yeah, I'm hoping we get there soon.
No, it's when I gave the neurosymbolic tutorial at AAAI this year, several people came up expressing a very similar, notion of neurosymbolic really needs its ImageNet moment to become real mainstream. Well, thank you both. And to the channel, that concludes part 2 of the interview. Stay tuned for part 3.